Question 62 is much like the previous question in that you're given a mass of a combustion analysis, so 5.214 grams, yields 5.34 grams of carbon dioxide, 1.09 grams of water, 1.7 grams of nitrogen, and then from that we're asked to determine the empirical formula and then eventually the molecular mass of this compound based on those numbers. But this is a challenging calculation because, again, they don't give us the moles of carbon or hydrogen or nitrogen or oxygen. We have to break that down from the masses of carbon dioxide, water, and nitrogen given. So we're going to start the same place we started the last calculation. We're going to start with 5.34 grams of carbon dioxide, 1.09 grams of water, 1.7 grams of nitrogen. And remember, we can't do anything with grams, but we can with moles. So I know for every 1 mole of CO2, if I go to the periodic table and look up carbon and 2 oxygens, I would need 44 grams. For 1 mole of water, right, I would need to have 18 grams of water, and then for 1 mole of N2, I would need to have 28 grams of nitrogen. So grams cancel out, and I'm left with all 3 of these now in moles. So I have approximately 0.1214 moles of CO2, 0.0606 moles of water, 0.0607 moles of nitrogen. And from there, I need to find out how many moles of carbon do I have, how many moles of hydrogen I have, and nitrogen that I have, because it's the carbon, hydrogen, and nitrogen that came from the molecule that went through the combustion analysis, not the carbon dioxide, not the water, right? So I need to work backwards to find out how much carbon was there, how much hydrogen was there, and how much nitrogen was there. So I know from every 1 mole of CO2, right, there's 1 carbon. For every 1 mole of water, there are 2 moles of hydrogen, and then there are 2 moles of nitrogen for every 1 mole of N2. So I have approximately 0.1214 moles of carbon, 0.1212 moles of hydrogen, and 1.214 moles of nitrogen in this sample. So just like I did before, I need to now find the mass of carbon, the mass of hydrogen, the mass of nitrogen, subtract that from the total mass to find what's the mass of oxygen I have remaining from this sample. So my 0.1214 moles of carbon, 0.1212 moles of hydrogen, and 0.1214 moles of nitrogen. Turn that into grams of carbon, hydrogen, and nitrogen. Right, 1 mole is 12 grams of carbon, 1 mole is 1 gram of hydrogen, and 1 mole would be 14 grams of nitrogen. So I should have approximately 1.457 grams of carbon from that sample, 0.1212 grams of hydrogen from that sample, and 1.6996 grams of nitrogen from that sample. So the whole sample weighed 5.214 grams. I'm going to subtract 1.457 from the carbon. Right, this is my total. Subtract carbon, subtract the hydrogen, 1.212, subtract the nitrogen, 1.6996. to find that the remaining mass is approximately 1.936 grams of oxygen. So just like before, I need to convert grams of oxygen into moles of oxygen to compare it with the other moles that I have. So 1.936 grams of oxygen, 16 grams for 1 mole of oxygen. I have approximately 0.1210 moles of oxygen. So hopefully you can start to see a trend here, 0.1210 moles of oxygen. These are all very close to a 1-to-1-to-1 ratio here. So you might at this point guess that the chemical formula, right, the only chemical formula from the left that matches this possible ratio, 1-to-1-to-1, would be this 3-to-3-to-3-to-3 ratio. But just to confirm, we're going to determine the mole ratio for this. Right, so if I divide all of these by the smallest number, divide all of these by the smallest number, divide all of these by 0.1210, we should see a mole ratio of carbon, hydrogen, nitrogen, and oxygen of 1-to-1-to-1-to-1. Now we need to compare this to my molar mass, right? I've got my empirical formula. I need to find my empirical formula weight. So the empirical formula weight, carbon is 12, plus hydrogen is 1, plus nitrogen is 14, plus oxygen is 16. That empirical weight is 43 grams per mole. The whole molecule weighs 129.1 grams per mole. Divide that by 43 to see it goes in there 3 times. So that means I need to take the empirical formula and multiply it by 3 to get the molecular formula of C3H3N3O3, or choice A that I hinted at when we saw that our initial molar amounts were already very, very close to the same number, right, giving us that 1-to-1-to-1-to-1 ratio, or the ultimate molecular formula of C3H3N3O3. Again, these two problems are probably the hardest types of calculations that you would see, the most involved, most in-depth calculation.